than the common crawl one, which corpus is extracted from common crawl, and for some tasks it fits better, and this highlights that if one should make some attention on doing things right and to be used in more places, not just language model and not just the size would matter, and then one should start from the beginning and not cleaning the bad corpus, for example. That's it.
Now let's thank again our speaker for this nice lecture. And our next speaker is Natabara, Máté, Gyöngyössy.
Can you hear me? Okay. So thank you for Balázs for giving me the, let's say, the prepared ground for this talk. I won't talk about my own research. I will give you a review and some takeaways again, but I would be more focused on the architectural and technical methodology rather than the whole field's overview. And about me, I'm a PhD student at the Department of Artificial Intelligence at Máté. I'm working on NLP projects in the applied perspective I've been working on these for like 6 years. And now we are trying to ramp up our research and education in language modeling in partial cooperation with Balázs's department, where we can have some joint forces from the technical and the linguistical and humanities side. So let me start really quickly. I will talk about large word models instead of language models. You will see that this is a buzzword, but it has some extra meaning behind it. And we can really quickly propose the first question: how do we model the word? How to model the word itself? And this could be answered really easily by language, by natural language. So we model our world with natural language in our everyday life. We use a symbolic sequence, which we use in a context-aware manner. And this sequence could be ambiguous, and this follows a given structure and conveys meaning. That's what Balázs maybe described in an even better precision. Okay. We use language, but have you ever heard about the Chinese room problem? Have you ever heard about the Chinese room problem? No, okay. The idea of the Chinese room problem is that you put a person in a room with only 2 windows. And he has a book inside which describes all the grammatical rules of the Chinese language in Chinese. Let's assume that this is a Hungarian man put into this box. And then he receives some input and has to output something. And based on the almanac of the whole Chinese language, he can kind of infer what the output should be for a given input. But he never really understands what is going on. So he has no grounding of this whole problem. He cannot connect it to, I don't know, an image of a tree or something like this. So we want to ground our language. And there is no solution in semantics right now. How do we ground our abstraction of language as humans? There are maybe 4 main branches. I'm not really deep into semantics. So please, if you have any comments and critique, then go for it. I was using Deacon's summarization for this, where he describes 4 stages of, or 4 different parallel theories on how do we perceive language. First one is that when we are observing or perceiving language, we recall an internal representation, an internal mental image of it. And the idea here is that language is totally learned from external signals. The second idea is that we are having some kind of a network-like association between the perceived signals by other modalities and the language modality itself. Then here is Chomsky's universal grammar theorem, where he states that we have some innate grammar, which is a universal grammar, and we somehow try to reflect this universal grammar, this universal way of thinking to our human language. And then we do inference based on this. And then the fourth one, which is Pinker's most prominent theory, is that we have an internal language, and we just try to translate our internal language to any other external language. So how does this all relate to LLMs and AI? Associative mappings are the closest to how language models are trained. We don't know if we are doing the same or if we are doing something similar, but these associative mappings are the closest ones. Transformer circuits, it's a really interesting field. It tries to discover these mental images inside the language model. It tries to infer rules or representations of, let's say, time inside the vectorial embeddings of large language models. So it tries to find these models which are inside it. Ongoing research is really eager to incorporate an exact universal grammar into large language models, because then we could make sure that there could be proper reasoning inside these large language models. If you have seen the posts which were rising up around the OpenAI scandals of Sam Altman and all the others last year, there was this mysterious project which they denote as Q star. And this, from the interviews, we can assume that this has some connection with proper symbolic reasoning in large language models. That's the holy grail right now. I'm not sure if this is achievable at all. And then translation to and from large language models already existing mental language is one of the hottest solutions for extending a large language model with different modalities. So these principles are all used in our AI systems. So what is the backbone for large language models? We have a few key characteristics. They are context aware. This is likely related to the attention mechanism. Who has ever trained a transformer? Hands up, please, just to. Okay, then I will go into the details of these transformers just a little bit. Then the second characteristic is that we have self-supervised learning. So as Balázs has shown, we are just masking out some data in different manners, and we don't have to label but manually. And we can kind of learn a good baseline from these unlabeled data sets, and then we can refine it. Then autoregressive generation is one of the most prominent techniques for generative models, where we basically model continuation probabilities over a sequence. And of course, large scale is in the name. We are talking about 1 billion to 2,000 billion parameters nowadays. From these 2,000, usually a few hundred are active parameters, but we will be back to that. So what is this dynamic selection? What is the mechanism that helps us in providing this context awareness? It's basically the famous dot product or multi-head dot product attention, where we have two sequences, or maybe just a single sequence, but different projections of it. And we try to weight or try to adaptively filter or highlight parts of this sequence based on some learnable similarity metric. So we are learning these mappings. These are feed-forward layers, if you mean. And by learning this similarity metric, the transformer architecture or attention-like architectures can highlight dynamically the most important information based on the input. So this is kind of close to meta learning when we are learning the procedure and not the output. Of course, it's all driven back to classical and normal supervised learning. And self-supervision is also really important. We are using these distributional semantics approach where we say that words that occur in a similar context are semantically similar. It's kind of true for even the Hungarian language. And the meaning of a word could be inferred from the context it appears in. There are two ways of modeling. One is the bidirectional or film-esque style modeling, which Balázs also highlighted. Here we can get future word semantics or future word information into our representation. The other one is the causal version, where we are moving for the autoregressive or predict the next style GPT-like modeling, where you get where you basically mask the last token all the time. So this is the language model recipe all in all. You have a symbol sequence, you somehow vectorize it with an embedding, then you perform, usually alternating, but you can do any kind of combination of temporal mixing. Usually this is a dynamic operation, and you use point-wise mixing to mix the embedding vector channels, basically. And then you use a last layer or some kind of other mechanism to select a token based on the last output vector. This selection is usually done by normal classification, softmax, and then you are taking the, I don't know, most probable one or just sampling from a probability distribution. And then you get your generated symbols, and then you do it again and again if you are going for an autoregressive task. And you are doing it in one step for all the masked out entities if you are going for a film-mask-like training. So I would say this recipe kind of outlines all the possible large language model configurations. Maybe some of them are not captured by this. This is the baseline. So how does a GPT model work in this way? We have our input sequence, then we have an embedding for vectors, then we use a multi-head attention, which is masked for causality, so it cannot see the future tokens, which we provide for the training. Then we have the feed-forward network, which performs the channel mixing. And then we just alternate for n layers. And in the end, we apply a linear layer and the softmax, which in the original GPT was just the transposed version of the embedding. Nowadays, they are learnable separately. And the interesting thing is that we use this kind of character engram or subword-like tokenization. And we use an algorithm nowadays, which is called byte pair encoding. This byte pair encoding is just like an optimal compression algorithm for language where the base symbols are characters or bytes which characters could be represented with. And then you are trying to find the most frequent pairs in your corpus. That will be your new vocabulary entry. Then you reevaluate your corpus, find the most frequent pair again, and do it again and again and again until you get, I don't know, 100 entries. Sorry, 100,000 entries. Sorry. That's it. And this autoregression happens with a high order Markov assumption most of the time, except some dynamically changing context windows. But most of the time, you have a fixed context window. If you use ChatGPT, then you have a maximal amount of words you can input to it. And this language model is trained on this case order Markov assumption, as you can see here. Predict the next word based on all the previous one in a context of at most k elements. And the sequence level probability is then decomposed with the conditional probability chain rule. So that's how it works. There are other alternatives for it. You have selective state space models. Maybe there will be some really similar presentations after the break, if I have seen the titles and the abstracts correctly. The idea here is that you have a state space model as you would have normally, and the state space model changes the input and the output weighting matrices and the time discretization coefficients based on the input. So there is some selection mechanism in it. It's again dynamic, just like attention was. And then you have some other linearly or compatible with linear representations where you have a set decay rate in this attention, And because it has a set decay rate for all the different steps, you can just find an equivalent recurrent representation, and then the complexity of inference will decrease. So these are all interesting ideas. Here comes the question of how could deep learning research benefit from these large language models, aside the really naive approximations, like, I don't know, you just ask ChatGPT how to write PyTorch. It's totally possible, it helps a lot. But how could we as a research community benefit from this? So we have to ask the age-old question, what have the Romans ever done for us? And why do we ask this question? Because most of this research is undoable in Hungarian. So OpenAI just, and Microsoft just builds a new data center which costs the entire Hungarian GDP for 1 year. That's something you cannot match. So let's start with the most aching problem, which Balázs also outlined, that you don't want to label a lot of data. And you definitely don't want to handwrite correct answers. That's really bad. How can you annotate data really easily? You can have preference data. You can have A/B testing again, but on the same model or on different models. And you can collect good answers and bad answers. Basically, you can have a ranking of these answers. And the problem is that if you imagine that you have to come up with a solution that is a good approximation for 100K words long sequences, how sparse your data would be. You won't even cover 1% of all the possible human language combinations. The thing is that we are also teaching with so-called training with teacher forcing, where the model is not incentivized to explore alternatives. You just provide the correct label, which is in your really sparse data set. And for example, in Hungarian, you cannot substitute kutya with ebb because there will be a penalty. But of course, it's really the same. So we use a second training phase in these cases, which is a sequence level preference training. And this fine-tuning procedure was the big leap that produced ChatGPT at the first place. So how can we basically imagine this? The first intuition is that in order to rank language, you have to understand language in a close to human level. So first of all, you need to create a reward model, which is a large language model itself, because it has to be a close to human level of a language understander. And in this case, you basically just train this reward model to output the ranking or the preference scores for an input-output, a full sequence input and full sequence output pair. And you train your policy network, your now in training ChatGPT similar model, to maximize this reward given by the reward model, but also being kind of true to its reference output. So trying to be as much of a good general language model as possible. And we use the KL divergence to kind of make it similar in this case. This was the case for a year or so, because the year after, people came up with the direct preference optimization methodology, which basically creates a boundary function for this optimization based on maximum likelihood. The idea is that now you take your new model in training and your reference model in training, and you want the probability output by the new model to be high for the winner sequences, and you want the probability output by the new model compared to the reference model to be low for loser sequences. And that's an easier way to basically turn this whole reinforcement learning procedure into supervised learning. And then early this year, we met with the odds ratio preference optimization, where the idea is that you don't even need a reference model anymore, because you just calculate the odds based on the policy model. And when the odds is high, and you just calculate the ratio of the winner and the loser sequence odds values by this model, and you optimize by this. So you don't need to keep 3 models in memory. Of course, one is only training, so you need gradients for 1 model, but you have to keep 2 models in memory as well, which would, I don't know, consume 16,100 GPUs. That's a lot. And inference time wise, it's also a lot. So instruction fine tuning is one of the gifts the Romans gave to us. And then the second one is, here you can see an overview of these. So basically supervised fine tuning on different language modeling tasks. Then you train a reward model, and then you keep the reward reference and policy models in memory. Then DPO gets rid of the reward model, and ORPO can just fuse all this procedure together. The second thing which we got from large language model research, or mainly large language model research, is flash attention. Flash attention is basically a GPU-aware definition or implementation of the attention mechanism. I urge everyone who uses transformers to write this line at the beginning of any PyTorch codes, because it can make it like 2 or 3 times faster. So just enable flash SDP scaled dot product attention. That's the idea. It's available in PyTorch 2 point something. And flash attention basically parallelizes the processing of the QK and the softmax calculation in a way that it never lets the whole intermediate result materialize in the HBM memory. So HBM is you know what HBM is, I hope. Okay, so basically this was kind of new for the NLP community, maybe for GPU specialists it's not that new. The idea is that you have 3 layers of memory when you are working with a GPU. The first is the main memory of the CPU based systems RAM. The second is the HBM memory, which we usually call the GPU's memory. And then the SRAM is the cache of the GPU, basically, or you can think of it as the cache of the GPU. And the cache of the GPU is around a few megabytes only, but it has an I/O speed of 20 terabytes per second. And compared to this, the HBM, the really fast, blazing fast GDDR5 memory is 10 times slower. So the idea is that you usually write the matrix multiplications result back to this HBM memory, and that's a lot of time. So instead of writing the intermediate results back to memory, and maybe even storing the forward pass results in the memory, you just drop the forward pass results, and it's faster to calculate it again in the backward pass than to store this whole thing in the memory, in the blazing fast GPU memory. So that's the state of the art now. And of course, people also wrote a kernel which fused all these together, and then you can get a better backend. So this is what the command I showed you enables if you have a compatible model. And also flash attention 2 works with the hierarchy of the process triggering in the GPU, so it's even better. We also have adapters. How many of you have ever transfer trained the model? When you just cut the last layers and then retrain it, or no one? Okay, then in applied deep learning, it's really a huge technique that, I don't know, in 2015 or 16, we had these ImageNet winner models. Everyone was really happy that, I don't know, there was this VGG, inception, residual networks, and so on. And the idea was that you just retrain the classifier on top, and then you're good to go. But in this case, you are not letting the intermediate layers learn anything. And nowadays, adapters, especially low-rank adapters like the LoRa and the 1000 versions, which has actually been developed from this, are solving this problem by training a small kernel space weight matrix in parallel with any weight matrix you have in your neural network, essentially. In this way, the intrinsic dimensionality of the problem, which the 3 parameters can learn, and these A and B will learn after the initial values, that's kind of limited. So if you have a small amount of data only, then it won't overfit, because you can kind of play with this. And the interesting thing is that it's much more efficient than training the top layers. So basically, by training 1% of the parameters, you can get a 99% full fine-tuning result, or 98, if I'm not mistaken, at least in language modeling. But you can read the paper here. And the really good thing about it is that you don't need half a terabyte of GPU memory just to fine-tune a model. You can choose the size based on the problem dimensionality you have. And the second good thing is that if you have ever heard about the bias trick in deep learning, then the idea is that instead of just adding +1 at the beginning or +b to have the offset parameter there, you just kind of extend your input matrix and then virtually aggregate it to a single supermatrix. Basically, you can do the same here. So you can fuse the learned weights into the original weight matrix because this is a parallel addition. So it won't cost more time in inference. Then came the idea of ensembling models, which wasn't new, definitely, but it lives a renaissance now. Basically, the idea is that you can train different separation models on different parts of the data set. So if you can see, in this case, the orange and the blue are separated by one submodel, one expert. The red one is separated by one expert, and the green one is separated by one expert, and they are locally well-trained experts. And the idea is that you can just put these experts in a neural network and then let the neural network handle the selection or the clustering of the data and find out where it should train experts. So the idea in the new language models, GPT-4 and up, works in the same way, is that you have a set of tokens, and each of these tokens are routed by a learned routing function to a given expert, which is just a small part of the hidden layer. And it is processed in that way, and then all of the expert outputs are fused together. So this is a good idea if you have a large set of data to use these mixtures of experts or model ensembles in the neural case. One interesting thing is that if one of the experts gets loaded too much, then it will just drop all the outputs and will not process them. That's why you cannot get two consistent answers out of GPT-4 Turbo and up, even if you give the same input and zero temperature. So that's the underlying architecture. We also have speculative decoding, where there is a smaller model which predicts a longer sequence, and then the large model just validates it in one step. It can be achievable by Medusa heads as well, and it creates a 2 to 3 times speed up without losing any performance. And then comes prompt engineering, the in-context learning principle, where you can just have few shot examples, and your data could be originating from anywhere. So we have these retrieval augmented generation systems where the language model will try to semantically look up your most important or most corresponding data in your data set, and then loads it back to the prompt and generates information based on that. And reasoning and planning agents are coming. So this year we should expect agentic LLM behavior, where the agent can have a reasoning procedure, a planning procedure. It will reflect on its errors, and then based on the external results or the actions it triggers, it will do it again and again and again. And in this way, it can decompose really complex problems into simple steps. So that's where LLMs are at right now. So what are word models? Because I have been talking about LLMs for now. What are word models? The idea is that we can kind of do this for any modality. And for the 5 well-known senses of kind of vision, even smelling is kind of well explored. But there are other modalities which should be included in a model if we want to model the world. For example, motion, or any kind of any branch of physics could be there. It's now in the state of development. Interception, like having a inner state representation for a model, for a robot, for example. It's also in its baby shoes right now. And we have something which is kind of controversial and no one really touched yet, is the self-concept as a modality. So let's forget about these now. These will be the future, and let's kind of focus on the classical 5 non-human senses. And for these, there have been some research done. And the interesting thing is that even if we don't have data that can connect, for example, thermal signals with sounds, that would be really hard to connect or collect, sorry. Then if we have a spanning tree of modality pairs that have corresponding data which could align all of these modalities, then connections emerge. So if you check out ImageBind, they have a really nice web page, and there are some interesting ideas where you can search acceleration data based on text. And that's kind of a wide idea, but there is this connection which emerged from this spanning tree of different modality connections. Here is an example. You can have object detection based on sound, because all of these are matching, and you are just looking for the part of the image which matches the representation of the sound the best. So how can we construct a language model? How can we construct a word model from this? And the usual recipe, I'm not saying this is the final because this field is still hot and still moving, but the recipe nowadays is twofold. You have your original language model in the middle, but for this language model, you need a symbol sequence. Language was already a symbol sequence. Images are not symbol sequences, for example. So how should you work on this? You first need to train a reconstruction model, an autoencoder-like model, which learns a splitting and encoding mechanism, possibly with some discretization. And then it learns how to decode and unify an extended symbol sequence. And then it outputs back the modality. Usually this is a variational autoencoder or a generative adversarial network. Basically, the training here constitutes of showing a lot of images, projecting them to a low-dimensional symbolic space, and then trying to restore the original image, for example, or the original modality input from that given symbolic sequence. And then you just have to mix these symbolic sequences from all the modalities and fine-tune your language model a little bit. And at that point, you have made a connection between at least 2 modalities, maybe even more. So here is one of the first examples, Lava, which is Llama plus Vision. And it uses an LLM and a clip-like vision encoder. This clip was trained on matching or aligning the embeddings of text and images. And the idea is that you have your image, you have a vision encoder, you have a projection in the end, you don't even have discretization at this point. And then you just patch your image to small slices, and each slice will have a token, a vector at the beginning of the input. If you remember, this was the case where you could only put a single input for the ChatGPT vision model. Now you can input multiple images, but back then you could only put a single image for each message or conversation because it was trained to handle it in the prefix only. And then language modeling comes. So if you have a question like, I don't know how many cats are in the image, then the correct answer will be there are 2 cats or something. So you just do the language modeling again. And you can do this for interleaved sequences with proper decoding of the other modalities as well. So if you have an image encoder and an image decoder, and then you can just interleave information from all of these modalities, use your good old large language model, which is now called a multimodal large language model or a large word model. They haven't finished fighting on the naming conventions, so that's the case right now. And for example, this Cody model can do, like, I don't know, summarizing, generating toned audio, recognize speech. And the interesting thing is that when you ground all of these modalities together, you get a better result than single modality models. So they will get better even in language understanding, and they will get better in image classification, object detection, and whatever, because all of these modalities ground together, and they get a little bit more robust to all of these errors which are in the bad quality data. Video, and then the language model will understand that, okay, now there's a man harvesting some apples, and that's already here. It will be on your Windows 12 computers, so we are not so far away from this getting into our everyday lives. And then it can also output some images and audio, maybe. So you can say that given a set of pictures portraying your neighbor's cat, here are some images, create a video and the sound of this cat, and then it will just create a series of images which can be DALL-E 2 was basically just a language model stuck in the middle of 2D fusion encoders and decoders, and that's it. You can model time series. That's really important, and it might be important for time series analysis. But Google has just 2 weeks ago uploaded, I think, time series foundation model. So you can fine tune it with adapters or any other way. You can model motion of people, and you can ask questions, or you can connect, semantically analyze motion as well. And you can also generate 3D objects from 2D slices or images based on these techniques just by using the recipe outline. Oh, sorry. I'm really sorry. Outlined here. So this is what is the fancy stuff right now. And that was all I wanted to say. So thank you very much. And I will upload all of the references so you can read through them if you want to read some good material. Thank you.
Thank you very much. And it's time for questions.
You mentioned in the beginning of your talk this picture, somebody sitting in a room and just reading Chinese books and creating characters. Do you think that this type of multimodal, or how about large word models, which you have mentioned, may solve this problem, make even give deeper insight for these models
Definitely.
for the world?
Definitely, it can be already checked on benchmarks that they are much better in grounding. The question is that can they reach human level, and you need to go to a church basically to find an answer for this. So we don't know if we are better than these models yet or not. There are some debates on this, but it's kind of philosophical and in the domain of theology. So we don't know yet, but yeah.
Thank you. So at the beginning of your talk, you motivated that, okay, how will these large language models or AI models understand the world, or something, or approach the human level? But are we really closer? Because all you talked about was like fusing multiple modalities of sensory input, like sound, pictures. And okay, those perform better, but the unique feature of humans is that they have some kind of memories. Your starting example, like reading a book, having more than 100,000 words as input, we still have the context. Have AI improved in that aspect, or what do we need to do and research to achieve that?
So the available context of these models is approaching 10 million tokens. That's roughly 5 million words or maybe 3 million words. So you can books into it. Google made an experiment last year where they went for an extinct language, and which was definitely not in the corpora of all of these, because there were some Amazonian tribes involved with no internet corpus available, and they digitalized a dictionary and a grammar book, which was done by the anthropologists who researched this tribe, fed it to the model, and then tried to engage in conversation in that Amazonian tribal language. And the language model could get to, I don't know, around 80 or 90% for that model's, so for the human translators capacity. So in this case, our experience is kind of replaceable and dynamically loadable to the context of these models. What is missing is the symbolic inner modeling. So this symbolic inference and the continual learning is kind of future works. Maybe I have just jumped over this slide. I'm really sorry. But the idea is that that we don't know how to achieve the universal grammar theory-like reasoning capabilities right now. There is some research going on, for example, for automatic theorem proving. We have some excellent Hungarian researchers in this field as well. So I think there will be improvement on this, but we are still not there. So our experiences can be replaced. The problem is more like the continual and symbolic experience.
Let's thank again for our speaker. And now the discussion will continue with the break.